I'm going to talk about computation using a data flow engine, and I'm in the EECS department at MIT, but for this year I've actually been at the startup company called Databricks that is commercializing the engine I'll talk about, which is Spark. So I've been trying to see how people actually use this in practice as well. So I'm going to go through a bunch of things in this talk. So first I'm going to say what I mean by a data flow engine. It's basically a number of systems called data flow that have arisen recently for large-scale data processing. And I'll say, okay, what's different? Why are people developing new systems to process these things? And then the main example of a data flow engine is MapReduce. So I'll talk about the limitations of MapReduce for numerical algorithms in particular. And then I'll present the Spark computing engine, which is an open source computing engine started here at Berkeley that addresses some of these limitations. Finally, I'll talk about doing some numerical computing on Spark, and I'll talk about ongoing work. So I should also say, just up front, I'm primarily a computer systems person, so I'm not algorithms or numerical person. So I'll be focusing mostly from the systems angle, but the goal of these systems is to make it easier to write a wide variety of computations, and these ones, the numerical, machine learning, statistical ones, are very important for that. So let's start with this one. So basically the reason we have these data flow engines is because in many domains data is going really quickly, and that's why we're here with the massive data sets. And so the only solution we have to actually compute anything on it in time is to parallelize the work across large clusters. And this has been widely adopted pretty much throughout the industry. And so the question is, how do we actually program these large clusters? The traditional way of programming distributed applications has been message passing, and this is an example of this is MPI. And this is a really natural model. Basically, you write a program on each machine and you have them send messages to each other. It makes a lot of sense. But unfortunately, it's very difficult to do at large scale. And there's a few reasons for that. So first, when you go onto a large cluster, you have to decide how to split the problem across the nodes. If you don't split it up correctly, if you don't take into account data locality and the shape of the network, what's near each other, you're not going to get the full parallel efficiency. Second, the larger you scale the cluster to, the more likely you have to have nodes fail in the middle of it. And when you write a program the MPI way, or just in general the message passing way, it's really hard to handle all the cases of something failing. And finally, even if a node doesn't fail, another problem you get at large scale is some nodes are just going to be slower than others for whatever reason. Maybe they run into some temporary problem, who knows what it is. And again, traditional message passing code kind of assumes that everything is in sync, and it's really hard to modify your application to deal with these problems. So because of these reasons, in the large data centers you have today at Google, Amazon, and so on, message passing is very rarely used. It's almost never used to write these large applications because it's just too difficult to use it for this. So instead, what has emerged is called data flow models. And data flow models restrict the programming model slightly so that the system can do more of these distribution tasks automatically. So basically, you don't get the full freedom of passing messages across any nodes you want, but instead the system handles faults, handles stragglers, all that stuff for you. And in these models, you express your computation as a graph of high-level operators. So you get a bunch of operators, map and reduce are some of the most common ones, that just say, oh, apply a function to this data set in parallel, or maybe regroup the data in some way. They kind of say what needs to happen, but not exactly which machine does each piece. And once you have that, the system figures out how to actually execute these operators based on what's in your cluster, and it knows how to deal with nodes failing in the middle and stuff like that. So the most common example of this is MapReduce. I'm assuming everyone has seen some MapReduce. You just have these two operators, and there have been systems designed that know how to run this at large scale. So there's a bunch of numerical algorithms that have already been written on MapReduce. There's a lot of work also on analyzing computational complexity if you're restricted to MapReduce and stuff like that. So things like matrix vector multiplication, this is used in, as a step in power iteration, or algorithms like PageRank is very common to do on MapReduce. Gradient descent methods for optimization, all kinds of them you can implement in this model. There's special ones like stochastic SVD is a way to do an approximate SVD that only takes 3 MapReduce passes or something like that. So it's designed to run really well in this specific model. Tall and skinny QR decomposition is another one that came out fairly recently that's designed for these commodity clusters. And many more of these exist. So people have started to do even this kind of work on MapReduce. So why do practitioners want to use a data flow engine? Why should we look at them as researchers? There's really 3 reasons. One is the ease of programming. It's much easier to write algorithms in this setting, as I discussed, if you want to deal with scale in particular. And so if you figure out how to make algorithms work here, it's more likely that they'll work out, that people will actually use them. The second is wide deployment. These engines are already sitting out there in many companies, in many industry labs, and so on. So if you figure out how to do some interesting computation on them, many people can use these. Actually, a really interesting aspect there is that the data is often in a cluster that can only run these engines, and it's difficult to run something like MPI on. And moving data is very expensive. So you want to be running on the same cluster. And finally, these really scale out to the very largest clusters that is designed to have nice scaling properties where the larger you go, you still perform well, you still get good parallel scaling. And even in the high performance computing world, people are starting to look at failures as a bottleneck in scaling compute clusters further. So these kind of architectures or something like them may end up being used there as well. Okay. So that's been a quick tour of why, what are data flow engines, why should we look at them? And the most common one, as I said, is MapReduce. Next, I'm going to talk about what are some limitations of MapReduce for numerical computing in particular, and then why we're developing new engines. So basically, MapReduce is really good at one pass of computation, where you do some work locally, then you aggregate some results. But it becomes very inefficient when you have multi-pass algorithms. And a lot of the algorithms we want to do in numerical computing do need to make multiple passes. So basically, there's 3 reasons why it's inefficient. So the first one is that you need to share state across the passes. And in MapReduce, there's no abstraction for storing state. Instead, you have to save your state to a distributed file system and load it back in the next MapReduce job. So if you have a computation that you can't express as a single MapReduce step, you spend a lot of time reading and writing out state from this distributed file system. Using the file system is slow due to basically the way it achieves fault tolerance, because every time you write data to it, it replicates it to multiple machines, it saves it to disk. And being a distributed file system, it can't do anything smarter than that for fault tolerance. All it can do is replicate it, and that's often more expensive than actually computing the data, is sending it out across the network. And finally, there's no control of data partitioning and placement across the cluster. In MapReduce, again, if your state is in this distributed file system, all it is a bunch of bits, and you can't tell the system how to place state to minimize communication in your algorithm. Just some pictures of this. I'm going to show two examples of things you might do. So first at the top is an iterative algorithm where the input of each, the output of each step becomes the input for the next step. So something like PageRank would look like this, where you keep updating this vector over time, and that's kind of your state. And so in this one, basically each time each blue box here is a MapReduce step, but each time you run one of them, you have to go and write out the state to 3 different nodes and wait until that's done before you can do the next step. Second one is imagine something like gradient, like stochastic gradient descent or something like that, where you run multiple passes over the same data. And even there, even though you're running passes on the same data, reading the data, maybe reshuffling it around to match the grouping that you want is going to be expensive. And so when you write these algorithms in MapReduce, which a lot of people do, they often spend most of their time just doing I/O, not actually running your numerical computation, but just writing data across the network or reading it from disk. And so basically these bottlenecks really slow down these algorithms. I'll show one example in more detail, which is PageRank. So in PageRank, and this is kind of the poster child sort of MapReduce application. In PageRank, you have basically a sparse matrix, and you repeatedly multiply it by a vector to compute the page ranks. And to do this, how are you going to do this on a cluster? You're going to have basically a file which is the adjacency list of your graph. So in that file, you have key value pairs, you have the vertex ID, and then the edges that come out of it. And then you have a second file, which is your current rank vector, vector you're multiplying that. And that's, again, a bunch of key value pairs with the ID of the vertex and its current rank. And then you're going to do these MapReduce steps. So in each MapReduce step, you group together the neighbor list and then the rank for each vector. And then you send out new messages to its neighbors, essentially, to update them, so to sum that up over them. So at each point, you basically have to hash together the data by vertex ID. That's what the reducing part of MapReduce does, and bring these two things together. So most of the data in both of these files gets shuffled across the network because you don't have any control of how the file is laid out. Stuff about a vertex could be anywhere on there. And you keep doing these iterations. So on each iteration, you join together these two data sets. Okay. So so basically, what's bad about this is if you look at that neighbors file, that never changes. That's just the adjacency list of your graph, never needs to change. But nonetheless, on each iteration, you have to hash together these things and send most of the data across the network to group it together with, with the ranks. So as a result of this, you have this communication cost, which is basically proportional to the size of your graph. This is the biggest thing in your problem. And it's also happening on each iteration. So it's actually proportional with the number of iterations. So the takeaway here is, when you use MapReduce for this kind of algorithm, it's not just inefficient with some kind of constant factor, like, oh, it's going to disk maybe instead of being in memory, but actually it's also asymptotically worse in terms of communication costs than you would have needed to do with a parallel machine. So even though it's simple and fault tolerant and so on, it has this problem. Okay. So I'm going to talk next about the Spark computing engine, which is one of the engines that's out there today that extends MapReduce and the data flow paradigm to deal with this problem. And Spark, as I mentioned at the beginning, it's actually a project that started at UC Berkeley across the street. Now it's an open source project with quite a few other groups contributing to it. So Spark extends the MapReduce model with primitives for efficient data sharing. I said earlier that the major problem in it was there aren't really great primitives for sharing state across steps of your MapReduce computation. And that's where all these inefficiencies, all this extra communication comes from. And these primitives in Spark are called resilient distributed data sets, or RDDs, and I'll talk about them later, but they're just a programming abstraction. Think of it as a distributed array or a distributed collection of objects, something like that. Spark is an open source project at Apache now. Over time, since the project started about 4 years ago, it's actually become extremely active. And now, apart from UC Berkeley, a number of companies contribute to it as well. And in the past year, actually, Spark has become the most active big data project at Apache, more active than things like Hadoop MapReduce or Giraffe or Storm or other projects like that you hear about in the open source computing space. So it's a really exciting time for the people working on it. And finally, Spark provides clean, easy-to-use APIs in Java, Scala, and Python. And these are important if you're prototyping something quickly, and also for users of this. It just tries to make this data flow model much easier to use. So quite a few people use it just for the API, not necessarily for the performance. But here I'm going to talk about the performance and what it brings to the table from that point of view. So the main idea in Spark, as I said, is these resilient distributed data sets, or RDDs. And actually, let me see, is this what this is probably the wrong slide. Let me skip over to the next one, 1 second. Oops, yeah. I just had a shorter version of the slide in there. Okay, so yeah, so the main idea is these resilient distributed data sets, or RDDs, and these are just collections of objects that are stored across the cluster. But the interesting thing about it is that users can control their partitioning, how they're stored, how the data is grouped across the nodes, as well as the persistence. So they can say like, oh, keep this RDD in memory because I'm going to run many iterations over it. There's no need to save it out to disk. So you get more control over how these are stored. You built them via parallel transformations. There's a whole bunch of operations you can use, like MapReduce, filter, and so on, that just create a data set from a previous one. And the system automatically recovers them on failure. So even though these data sets will not necessarily be replicated across the network or anything, you still get fault tolerance, and you actually get very similar fault tolerance behavior to MapReduce. Okay. So I'll show a little bit of what this looks like with just a short example you might do on log mining. So here I'm going to use Spark's Python API, and we're going to load error messages from a log file into memory, into an RDD, and then search for different patterns in them. So here's what, here's kind of the cluster that we'll be running on. So we have a master node called the driver and a bunch of workers. And then I'll show the code that you type in. One of the cool things about Spark is you can actually use it from the interactive Python interpreter. So you could just fire up Python and start writing this code and have a computation run on a cluster. So actually quite a few people use it that way just to explore data. Okay. So first thing we do is create this variable lines, which is a Spark text file, and we give it a path on a distributed file system. So here it's showing HDFS, the Hadoop distributed file system. And this is an RDD, a distributed collection of strings that we're going to then transform to do different things with. Okay. Next thing we can do is do some transformations. So for example, we have this log of data, and we want to figure out which lines of text contain error in them, and maybe we're going to load only those lines into memory and do something with them. So this is a transformed RDD, and the code there in red, the lambda, is the Python syntax for just writing a function in line. So you can just write a function in your Python program and pass it into Spark, and Spark will automatically execute it in parallel across the nodes. Okay, and we might want to do more operations. So for example, maybe these are tab-separated fields, and we want to pull out field number 2. And so you can do that with the map operation, pass it another function to extract that field. And finally, we can tell the system to cache some of the data sets in memory. So here we don't want to load the whole file or even the whole line of text. We just want to load the error message. So we just do messages.cache. Now, the way Spark executes, all these operations are actually lazy. So at this point, nothing's actually executed. Instead, it's just kind of built a plan of what it needs to do to compute this data. And when you actually need to compute it, you launch another type of operation called an action. So here we're going to count how many of these messages contain foo, and that count is called an action. It has to kick off a computation and return back a number instead of a data set. And when you do this, Spark actually looks at the previous ones and comes up with an efficient plan to execute all the steps so far. So in this case, it's going to first check where the data is distributed across the cluster. It sees, okay, maybe there are blocks of the file on different nodes. And then it's going to send tasks to each node to compute some results. And so they're going to do that, send back some results. And finally, each node is going to build in memory a cache of just the error messages that were sitting on that node. So just those partitions of the RDD. And we're going to get it back. So this execution here is similar to the execution you'd get in MapReduce, where it takes into account data locality and figures out how to get you the result. Next time you run a query on this, maybe foo wasn't the problem. That often means it's bar. So you search for that. So that's the next one. And Spark, when you do this, is going to know that some of these messages are sitting in memory, and it's going to just scan those and give you back some results, and not have to go back to scan the on-disk data and filter it again. And of course, you don't have to do just filters and counts. You can do a whole bunch of other operations as well. So to give you a sense of how this works, how much the performance improves, one of the demos we do of this is full text search of Wikipedia on something like 20 machines, and that's just scanning it and searching for text in a very brute force way. And when you do that with on-disk data, it will take about 20 seconds to do it, and when you do it with the cache data in Spark, you can do it in about half a second. So by controlling the storage of this data, by filtering out just the parts that you want, you can really make it a lot faster, and users can actually work with this interactively to explore data sets. So that's what that provides. Okay. The other aspect of RDDs that is powerful is fault tolerance. So when you build an RDD out of these transformations, it automatically remembers how it was built, and it uses this for fault recovery. So in here, I'm showing a slightly more complicated program. I'm doing a map and then a parallel reduce and then a filter. So basically here I have some records, and I want to count the number of records of each type. So I do that using the map and reduce to count up, to add up the values, like the one value for each one. And then I want to filter out just the records that have, that have a count higher than 10. So when I do that, Spark's come up with this dependency graph over here. It's come up with this dependency graph between the computations with how data was moved between them. And what's good about that is that if any machines fail, we can use this graph to recover missing data. So for example, if 2 of the nodes in the cluster fail, we lost part of our reduce, the things that group together data for those keys, and we also lost part of the filter output. And Spark is going to recompute just the missing pieces and give you back, the full result. So it can quickly recover. It doesn't need to go back and restart the whole computation from the beginning. And that's automatically provided by RDDs. And then the final thing Spark knows about is data partitioning. So when you run these operations, some of the operations group together data in a known way. So for example, when we do reduce by key here, that's bringing together all the records of each type, we know that and usually, to do this, you hash partition the data across machines. So we know that the result of the reduce is hash partitioned. That means that Spark knows that, for example, things with hash code, equal to 0 end up in the first partition at the top. Things with hash code equal to 1, mod 2 end up in the second one at the bottom. And it actually uses this information in planning future computations on it. So for example, now if you group this data set together with another one, it knows that it doesn't have to reshuffle this data across the network because it's already grouped in a known way. And in fact, even when you do things like filter, filter can only eliminate some records. It's not going to change the keys and the partitioning. So it knows that this data set is hash partitioned as well. So this comes in when you do things like the matrix vector multiply that I talked about in PageRank, where you want to group together one of the data sets in advance because you'll keep multiplying with it. Okay. So that's been kind of a quick overview of what's in Spark. So next I'm going to show how you can use it for some numerical operations, and I'll just show some of the simple ones built on top and how they end up doing better than MapReduce. So first thing I'm going to show is just iterated MapReduce, and this is going to be just logistic regression using gradient descent. And I'm just doing it here using batch gradient descent. So it's really basic. It's not meant to be the very best logistic regression out there, but it gives you an idea of how you can write these things. So in logistic regression and in these kind of algorithms, we basically have a data set, a bunch of vectors, and we want to keep running this parallel sum over them, essentially, and getting back a result. So it makes a lot of sense to cache the data set into memory across the cluster and reuse it, because we keep doing sums over the same data set. So if you write this using Spark, you end up, you basically can just take like a text file, for example, and pass through a function to parse it into a bunch of vectors. So this is some actual Python code you can use to do that. And then you tell it to cache that. And then you start with a random initial vector. That's the W here. That's kind of the parameter you're optimizing. And you just do these maps and reduces that compute the gradient function. So hopefully that's actually the gradient function for this thing. And at the end, you update your W, and at the end you can print out your result. So it's really simple. When you actually run this and compare it with something like MapReduce, it ends up running a lot faster. So this is just showing, based on the number of iterations we're going to run, this is Spark versus Hadoop MapReduce. And basically what you see is whenever you run this computation on MapReduce, on a disk-based file system, each iteration takes roughly the same time, which here is about 100 seconds. And so the more iterations you run, you take much longer. When you run it using Spark, the first iteration that parses and loads the data is 80 seconds, but then later ones are only 1 second. So this is what I was saying before. In these algorithms, 90% or more of the time might be going into I/O, not into your computation. And if you look back at this logistic regression one, the computation is really just a dot product in there. So it's actually really fast, and any kind of I/O you do is going to significantly slow things down. So that's one simple example. As a more interesting example, I'm also going to sketch PageRank, which is the problem we saw before. So if you remember before, in PageRank, we ran a number of MapReduce steps, but the problem was not only did we have to scan the data from disk on each iteration, which is one thing, but we also had to reshuffle it across the network each time, because we kept grouping together these these adjacency lists and the parameter vector, and that requires sending most of the data over the network and hashing it together. So here we're going to use cache to keep the neighbors list in RAM so that we don't have to read it from disk. And we're going to use partitioning in Spark to avoid repeated hashing. So here's kind of our initial data, the neighbors list and the ranks. And these are just files in the file system. So we can't guarantee anything about how they're partitioned. And these will be kind of our two initial RDDs. Next thing we're going to do is we're going to call partition by, which just groups the data together using some function. So here, just hash it together, so using the hash function we normally use in Spark. And we're going to create a new RDD from the neighbors. And we're going to ask Spark to cache that in memory. So now these neighbors are sitting in memory across the cluster, and we know that they're grouped together by key. So it's much more efficient to basically multiply a vector by them. And next, to actually multiply them together, there's an operation in Spark called join that just brings together key value pairs with the same key. So when you do that, Spark's going to actually execute it in a way that takes into account the partitioning. So it will know, because the data at the top, the neighbors are already hash partitioned, it's going to actually bring each rank to the corresponding machine for that hash code instead of regrouping the whole data. And as you run more of these iterations, it's going to keep doing that. So at the bottom, you produce new data, like the messages you send along the graph that you have to shuffle around each time. But whenever you join it with the neighbors, that never gets reshuffled across the network. So and it's going to keep doing that. So basically, just to recap the partitioning part, once you've grouped together sorry, things with, once you've grouped together the neighbors by doing the partition by, the data for each hash code is going to stay on the same machine. So for example, the red one, say these are things whose hash code is 0 mod 3. They're going to be on one machine of the cluster. The orange one is going to be on another one, the purple one on another one. And so we never have to send these adjacency lists around. And again, the adjacency list is usually much bigger than the vector itself that you're multiplying by. And so we save this, this communication cost on each step. Okay. Here's some of the code to write PageRank. I'm not going to go to it in a ton of detail, but my point is just that it's actually really little code. And if you try to write PageRank in something like Hadoop MapReduce or MPI today, that's going to be a lot more code than this one. So essentially, like in the previous one, we end up, we create some initial RDDs. And then we have these loops. Yeah, I'm just going to loop a fixed number of iterations. And then we join together. Join is the operation to bring together links and the rank for the same key. And then we do a reduce to add up together the new messages that these guys sent out. So that's kind of what the code is, and it's very quick to write this down. And in terms of how PageRank performs, this is one comparison with MapReduce. I think this is on some Wikipedia data. And basically, you have Hadoop MapReduce in blue. That's going to disk on each step. And it's also reshuffling the data across the network on each step. Then you have a naive version of Spark, one that doesn't do partitioning. So one that loads the vertices in memory, but still reshuffles the data on each step. And that's a little faster, but not super fast. And then you have the one where you use controllable partitioning as well. And there you eliminate much of the communication cost, and so you end up going quite a bit faster on each iteration. Okay. So based on this ideas of controlling the partitioning and controlling storage, we've implemented a number of other numerical algorithms on Spark as well. And some of them take advantage of these in more interesting ways. So I'm just going to sketch one of these here, which is alternating least squares. So if you remember, in PageRank, we really wanted to hash together the matrix because we kept multiplying it by a certain vector. The same thing is going to happen here because in this one, we keep grouping together and multiplying data actually in two different ways. So alternating least squares, is quick recap. You want to compute this matrix factorization that's low rank. You just start with some random low rank matrices A and B, and then you basically keep B constant and solve for A using least squares, and then you keep A constant and solve for B using least squares, and you keep repeating this process until you converge to some kind of local minimum. So that's what it looks like. So when you implement this on Spark, it's a bunch of these least squares computations, and there are some interesting tricks we use to make this fast. This is actually work that I did with Joey Gonzalez and Virginia Smith at Berkeley basically last year. So one of the things we do is, because you keep grouping data both by rows and by columns, we actually keep two copies of the matrix R in memory, one that's hashed by the rows and one that's hashed by the columns. And that means on each step, we never have to shuffle R around to regroup it. Instead, we only need to move the much smaller data sets that are in these low rank matrices to send these vectors basically to the machines that have the right slices of R. And we keep them cached, we keep them partitioned, and we actually also designed this to operate on blocks of the matrix to lower communication. And within each block, we can actually use single machine numerical libraries such as BLAS or something like that to make the local computation fast. So by doing this, we're able to get actually very competitive performance with C++ and MPI-based systems for this task. So this is alternating least squares on, the one in blue is on Hadoop using the Mahout library that Hadoop comes with for, for machine learning. The one in red is the Spark one that we did, which is actually written in Scala. And then the one in green was GraphLab, which is written in C++. So, this one here is a little, I don't know what. Okay. This one here is a little slower than GraphLab, but it's also 2 or 3 times less code, and it has fault tolerance. It can scale to very large clusters as well. So it definitely gets really close to the more optimal ways of solving this problem. Okay, and final thing I'm going to show is just one other quick algorithm, which is which is kind of a cool one you can do, which is Sparse subspace embedding. So this is one where we want to compute a sketch of a matrix A, and one way to do this is actually you multiply it by this, and A is tall and skinny. So there are many many vectors, but the number of columns is manageably small. And one way to compute a sketch for it that is actually small enough to fit on a single machine is you create this phi, which has only one non-zero element in each column, and that's chosen independently, and that one is just a Gaussian variable, and that's also generated independently. So it's a sketch that appeared in this paper at Stock last year, and I just wanted to show that it's really easy to write this kind of matrix multiply in Spark. So basically, here we have A is an RDD, or a distributed array of vectors. So just each row of our matrix is an element in this, and then we choose the dimension we want to work with. And then to do this matrix multiply, we basically just generate a random column and a random Gaussian variable on each one, and then we add them together. And so this is a way to run it that just runs computation locally. It's very fast and it's easy to write. So these are just some of the things that that you can do with it. Okay. And finally, I want to talk a little about what being able to do these computations in a data flow engine means for users. And that is that users can just use a single engine or a single tool to implement their whole parallel computation. So often, I focused here on just the numerical algorithms and their performance, but often these algorithms are part of a larger application that starts with just reading the data, maybe parsing it into features or something like that, then actually training a model, and then maybe querying it or doing further steps after the model is built. And if you use separate systems for these things, so most users are using MapReduce or data flow engines to do the first part, just the data transformation and loading. If you then have to use a different system for the numerical computing and then go back to a data flow engine for the querying, you end up with a lot of extra cost because of these distributed file system reads and writes that you do at the end of each one. And as I showed earlier, in a lot of these algorithms, the computation isn't that expensive compared to the I/O and communication cost. So if you use something like Spark, you can instead chain these together in the same program. Because you're using RDDs, the data can stay in memory between them, doesn't need to be replicated, and so on. And then at the end, you can either query it interactively, or you can write it back out to disk. So it's even though each step, like say the numerical step, isn't much faster than doing it using MPI, the pipeline as a whole will be faster because the pipeline itself consists of these multiple steps. So that's one of the things about this that is interesting for practitioners. Okay. So finally, in the last few bits of the talk, I just want to talk a little bit about ongoing work, what's happening in Spark, and then I'm happy to answer some questions. I'm going to talk about two areas of work. One is the open source world, and one is in research. So on the open source side, Spark actually has a really active developer community. It's grown a lot over the past few years, and as I said earlier, in this year, it's actually become the most active big data community in open source in terms of number of contributors per month, number of patches sent per month, amount of code added per month, stuff like that. So since the project started in 2009, we've had over 200 developers from over 50 companies contribute to it. And down there are some of the companies that either contribute to Spark or have products based on it. And in the past year, we actually surpassed the contributors of Hadoop MapReduce, which is the next most popular one. On the numerical and machine learning side, a lot of the activity has been in this built-in machine learning library we have called MLlib. So after building the core engine, we wanted to provide some libraries out of the box with a bunch of algorithms that use the engine and are designed to scale well to clusters. And we started this library in summer of last year, actually, or I think in September. And since then, we've gotten a bunch of these algorithms contributed to it. Right now, these are still fairly basic ones, but it's good. The really good thing is that they're all designed to scale out, and they take advantage of tricks like data partitioning and caching and so on to execute well on a cluster. So these are some of the ones down there. In MLlib, there's actually also a lot of activity happening now. And so I mentioned, earlier, I didn't go through all of them, but I showed some of the ones we have. Some of the things coming are sparse SVD for square matrices, which is actually, it's a pretty efficient implementation that's being contributed by someone from Twitter. Multi-class decisions tree, a statistics library. We're trying to use some of the more recently proposed algorithms for things like sampling, ADMM, and LDA. And as a researcher, what's interesting with these is if you want to start with a fast implementation of one of these and then modify it somehow, you can probably find one in MLlib. And also, if you want to contribute one to open source it, we're glad to accept contributions here. And it's a good way to immediately reach a lot of users and just to add your algorithm in there. So since the library started in September last year, we've had over 40 people contribute algorithms, and all of the ones up here are actually in progress right now, as in there's an open patch for them, and people are working to create them. Okay, that's on the open source side. So we're hoping to build this standard library of these algorithms. On the research side, Spark is also used in a number of research projects, and not going to talk too much about all of them. But in Berkeley, in the AMP lab here, there are a number of them built on it. Graphics, I think, had a talk at the conference earlier. It's graph parallel computation on a data flow engine, and it's actually doing that using Spark to be able to do a lot of manipulations of graphs. Spark R has an R interface to it. As part of that, they're also working to do efficient matrix math on top of this engine. So, some of the matrix decompositions and multiplications and stuff like that. Machine learning pipelines is an ongoing one where it's actually a higher level interface to define a pipeline of steps, and then it fuses together and optimizes all of these steps. I'll talk a bit about it later. And some applications in research include applications in neuroscience, in traffic, and in genomics. And these are happening at other universities as well. Just as a quick glance of one of them, the ML Pipelines project, which is led by Evan Sparks here, is letting users write a pipeline of different steps. So this is actually an image processing one on the right, using this very high-level API where you just chain together steps. You have a step and you chain it together. And once it sees a description of the whole pipeline, the system actually comes up with an efficient implementation. So it can do things like it realizes you're training 3 models at once, and it vectorizes that so that you do, say, one matrix multiply that updates all 3 of them at the same time. And it just does that for you. It figures out where you're going to share data, how to place it to minimize communication, and how to share scans across the data to make the whole pipeline fast. So this is one of the things that people are doing that's kind of in line with Spark's approach of offering these high-level APIs. And finally, Spark started as a research project. I think still the majority of the code is code that was just written at Berkeley by graduate students. And we've constantly brought in additions on the system side, new ideas that people have, and we want to bring the same for these numerical algorithms and machine learning. So if you have an interesting algorithm, a scalable one that you think would be interesting to try out, it would be great to talk about that, and maybe we can figure out a way to make it available through here, and again, to reach a whole bunch of users. So that's all I wanted to talk about. So in conclusion, I hope I've given you a sense of what data flow engines are. They're becoming an increasingly important platform for numerical computing. And in particular, if you have algorithms that run on them, a lot of practitioners can just use them out of the box on their existing data and clusters and just try them out. Early models like MapReduce were very successful at making programming easier, but are actually quite inefficient for a lot of these algorithms. And so work like Spark and other systems in this space are meant to address that. And if you want to learn more about Spark, you can find out about it at spark.apache.org. Yeah, good question. Yeah, so I guess the question is partly like, what are parallel algorithms that these data flow engines aren't good for? So the main thing that's a problem in these is basically the latency of the communication steps or barriers. So each time you do something like a reduce here or a group by, it's a barrier across the whole cluster because it's deterministic, and the result needs all of the data from the previous step to be computed. So if you're doing something, if you're doing something where you want to do an iteration every few milliseconds, and for example, a scientific simulation in MPI, that's pretty hard to do over here. If you do something where each iteration or each barrier is, say, every few seconds, that's usually fine. The system can deal with that and can do the scheduling to actually make that happen in time. So basically, it's when you have really fine-grained computation steps. Yeah, thanks.